Okay, so it's a real pleasure to have Guatam and Kamal from the University of Waterloo coming to speak. And he's going to tell us about CoinPress, which is some very exciting work.
Right. Thanks, Thomas, and thank you all for being here. Today I'm going to tell you about a really fun line of work. I think I found it very fun, called, which the latest work has been CoinPress, Practical Private Mean and Covariance Estimation. This is sort of, I'm a theorist a little bit by training, but I've been trying to move more towards, practical and applied directions. And this has been probably one of the more satisfying ones. I did the previous work with Jerry Lee and Vikram Singhal, which sort of laid the foundations in terms of theoretical works, but this is kind of the next step in terms of making it more practical. And then there's another step that we're working on right now to make it even more practical and applicable in more settings. But I'm going to sort of tell you this step. This was a paper which appeared in Europe's last year, 2020. And it's joint work with Sourav Biswas, who's an amazing undergrad at the University of Waterloo, Yihe Dong, who's a research software engineer at Microsoft, and John Ullman, who I'm sure many of you here know, who's a faculty at Northeastern University. So in one slide, the main setting we're going to be concerned with is, given a data set distributed according to some distribution, we want to estimate the mean of that distribution. Except now we want it with the additional constraint of privacy. There's many new challenges that arise in this setting, and kind of at a high level. One is, where does my data lie? We'll revisit this in a few slides, and I'll show you what the exact challenge is. And in this talk, I'm going to tell you about practical and general tools for private point estimation and confidence intervals as a sort of part of a bigger framework on private estimation. We're going to use mean and covariance estimation as sort of vignettes, but what I'm going to describe is really more general and can probably be used for private estimation in a variety of settings. In particular, we're going to be able here to do multivariate data, covariance estimation as well. And at the same time, on the sort of theoretical guarantees, we are going to give near optimal sample complexity for many of these problems. So, okay. I'm sure I don't have to tell any of you about what differential privacy is. I think this should be familiar to this audience. So I'll skip over the definition. I will say, though, that the notion of privacy we're using in this talk will be zero concentrated differential privacy. So for those who may not be familiar with the different notions of privacy, generally the most commonly known ones are pure differential privacy, or epsilon zero differential privacy. Then there's approximate differential privacy, epsilon delta differential privacy, where delta is greater than 0. You can think of concentrated differential privacy as sitting between those two. So it's stronger than approximate differential privacy, but weaker than pure differential privacy. If you don't like a different notion, then just note that everything I talk about today will pretty much hold for approximate differential privacy as well. Cool. Oh yeah, and of course, at any time, if there's any questions, anything's unclear, you want me to elaborate more on something, please ask. So today we're going to be focusing on privacy in a statistical setting. Let's talk about what the setting is more precisely. So we imagine that there's some distribution P, some population P as it's sometimes called, and via random sampling, we generate some data set x1 through xn. We feed these into an algorithm M, which is our algorithm, and we get some output Y. And we want this output to have high utility with respect to the distribution P, not necessarily with respect to the data set x1 through xn. And many non-distributional settings for differential privacy would focus on getting good utility with respect to the data, but here we really care about making inferences about the population, the unknown distribution. So our desiderata in this case are twofold. The first thing is the sort of non-private guarantee. We'd like the algorithm to be accurate, so stochastically with high probability over the data generating process according to this distribution. This sometimes requires assumptions about P to hold, say, for example, Gaussianity, which is kind of what I'm going to assume for this talk, but I'll also mention that it holds under weaker assumptions as well. And in terms of utility, that's a very general term. Well, we're going to be focused on L2 error in terms of a mean estimate. So that's the non-private guarantee. The private guarantee we're going to want is that the algorithm is private always. So for any realization of the data set, no matter how unlikely it is, we still want the algorithm to hold, we still want the algorithm to guarantee privacy because we don't want to compromise on privacy. And today we're going to focus on the privacy guarantee, concentrated differential privacy. And an overarching goal, like pretty much a lot of the work I do in differential privacy nowadays can be described as in this slide, just trying to understand what is the additional cost of privacy to guarantee 2 in addition to our non-private guarantee 1. Before we continue, are there any questions about this setting, or in an abstract sense, what we really want? Cool. If there's no questions about the desiderata, let's talk about this problem. This is a problem which arises in differential privacy, which doesn't apply in the non-private setting, which I'm sure many of you are familiar with, which is estimating sort of the range of the data. So let me give you an example, illustrate by example. Suppose we're given a set of, say, female heights x1 through xn. We want to compute the average height. It looks something like this. I picked just female because I wanted to be sort of a nice, well-behaved Gaussian for illustration purposes. So how would you compute the average height of a female based on this? Yeah, this is sort of a more formal definition. So non-privately, if you want to compute the mean, it's very simple. This is like stats 101. Just take the empirical mean, and this works in a wide variety of settings, right? This is the easiest problem in the world when you talk to a statistician. Yeah, not much to do, but it turns out even just this very simple type of question gets a lot harder under differential privacy. For example, this statistic, the empirical mean, as many of you will know, is not private because it has an unbounded sensitivity, which I'll illustrate more step by step here. So if you want to do it privately, what you can instead do is do the Gaussian mechanism, which adds noise to the non-private statistic proportional to the statistic's sensitivity. So now the tricky part here is obviously, so yeah, here's the Gaussian mechanism. Here's the non-private statistic. Here's the additional noise you have to add, where delta is the sensitivity of the summation. And you should, many of you should be familiar that the sensitivity of the statistic, if you're just adding numbers up, can be very large. For example, in this, if you're just looking at real numbers, then the sensitivity of the statistic of the empirical mean is going to be equal to like real max or real max over n, depending on what you consider the sensitivity. So the point is, just moving a single point can corrupt the statistic by an arbitrarily large amount, effectively, and you have to add essentially infinite amounts of noise, which would totally ruin your signal. So this is kind of course, silly because we're looking at the heights of humans, which cannot be 1.8 times 10 to the 308. So the way we get around this generally in differential privacy is instead using some sort of data or having some sort of way to find the range of where human heights lie and clipping our data to that range. So more realistically, what we would do is we would, in fact, say, okay, anything outside the range 120 to 200, that's garbage data, that's bogus, it doesn't actually exist. Instead, just either remove the point entirely or round to the nearest endpoint of this interval, 120 to 200. And then you can take the empirical mean and noise it based on this. So what we did here really was use prior information that we have about where the parameters should lie. For example, like just looking at humans, adult humans, you should know that they're generally between 120 and 200 centimeters tall. This is maybe a bit generous on both ends, but at least this is something that we know for sure. And that gives us some bound on clipping, on how we can clip our data. Now you might be thinking this is okay, but this is still a lot of noise that you're adding. You're adding noise proportional to 80 over epsilon n. If you tell that to like a data scientist or statistician, they'll tell you that this is way too much noise, that we're not going to get any good signal there. And you're kind of at a problem here because there's two things you could do at this point. You could either maybe go back and do more research about what data set you have, say, okay, maybe we can reduce it. Maybe most females are between 130 centimeters and 190 centimeters. That seems like a good estimate. But you can imagine that's still like, a 60 over epsilon n, which is a lot. And that took a lot of work, perhaps, to find out more data. This is a simple example like we're talking about, but you can imagine if you're doing some complicated biological data set where you have no intuition as to where the parameter should lie, where the data should lie, then we're not going to get very far. So the question we really want to is minimize the cost in our estimation procedure due to this uncertainty. So here we sort of know that the parameter lies in a range of 80, and we want to minimize the cost based on the value of this 80. Are there any questions about this challenge and this sort of thing?
What are these strange units that you're using in Canada?
Centimeters. You should be familiar with these, unless you've forgotten your roots. But yeah. Okay, let's continue with a simple example, like just to show you more quantitatively how this really affects the how this shows up in terms of a sample complexity or in terms of a rate bound. I want to quantify how much we pay in terms of our uncertainty. So here's the baseline theorem of what Gaussian estimation would look like. Suppose we have a data set where the data set's generated according to some Gaussian, would say identity, or just one variance, a univariate Gaussian. And we know that the mean is less than or equal to R. So this is kind of quantifying what I said in the previous slide, where we said the heights lie between 120 and 200. Well, similarly, we're going to say here that the mean is less than or equal to R. Really, we could have just said any interval, but I'm just keeping it centered at 0 for simplicity. So this this is an odd additional condition, but it's really necessary for differential privacy in most settings. So think of this as just being quantifying how much uncertainty the analyst has. If it's a very large value, that means they're not very certain about what their data looks like. And if it's smaller, that means they're already pretty sure what the parameter is about. So my claim is that there exists a concentrated DP algorithm which estimates the mean to this accuracy, 1 over square root n plus r over n times epsilon. So let's unpack this a bit. How is this good accuracy? Is this bad accuracy? Well, the first term here is a pretty good term. It's the non-private rate. So even if you didn't have any privacy constraint, this would be what you would get in terms of accuracy. So that's cool. The latter term is kind of the additional cost of privacy by this very simple algorithm I'm going to present in the next slide. So let's take a look at these two terms. You can see that the second term is a smaller term when n is rather large, because it decays faster than the first term. However, you can see that it increases linearly depending on how big r is. So in other words, if the analyst has a lot of uncertainty, then you'll pay a very high cost due to privacy. So this is kind of how you should think. It's a lower order term, but if you had a good control over r, but if r can be large, if the analyst is uncertain, then it can pay. Might have to pay a lot. And for those who prefer sample complexity bounds, this kind of says that the sample complexity is 1 over alpha squared plus r over alpha epsilon, which again can be large if r is large. So the algorithm in order to achieve this, if there's any questions, feel free to ask about this theorem. But the algorithm to achieve this type of guarantee is really simple. Essentially, it's just what I told you in the previous slide. You clip your data and then you add noise. So I'm going to illustrate how the analysis goes. But if you don't follow this, don't worry too much. It's not super important. So again, there's our setting. We're given a data set where we know that the mean is less than or equal to r. That's kind of the prior knowledge. And what you do is you clip or Windsorize your data. This should be a very familiar process to anyone who's done differential privacy before. Essentially, you say, OK, our data can only be so large. And in particular, how big do we take it? Well, how do we choose our clipping bound here? Well, what we do is we say, we know our mean is within plus or minus r. And Gaussian tail bounds tell you additionally that a point could deviate from that interval by at most square root log n, roughly, maybe with a constant in front. But essentially, what you do is you just widen your interval in order to make sure that all the points fall into that interval with high probability, and would have that a truly Gaussian data set is unchanged due to Gaussian concentration. But now the benefit is that the width of this interval is bounded, so we can add a finite amount of noise. So the way the analysis works isn't too tough. I'll sort of skip over it a bit, but you just take how much non-private error is there, 1 over square root n by Chernoff or Chebyshev. We say, importantly, that sensitivity now is bounded to be r over n, roughly, maybe 2r over n, maybe 2r plus 2 root log n over n, but basically 2r over n, and you can add noise proportional to this r over n, r over epsilon n. Because the standard deviation of the noise is that large, that implies that the error that you get is r over epsilon n as well, and therefore the overall error you get is the non-private error plus the private error. There's nothing too fancy going on here. If you didn't follow, don't worry about it. But yeah, it just says that this is where the error comes from. So it seems like a lot of error comes from this latter step in particular, where we just do the clipping and add noise because it's still relatively wide. Cool. So that's how the analysis goes in this sort of very simple case. This slide is the most important slide of the talk, I'd say. If you understand this slide perfectly, then you could fill in the details, I'm sure, for the rest. It's a very simple modification to what I've told you already, which turns out to be highly practical and does very well in these settings. And yeah, I think it can have more applications than the sort of mean estimation and covariance estimation that I'm talking about today. So this is an approach via shrinking confidence intervals. And I'm going to describe the type of setting it works in first. It's going to be described minimally in the sense that I'll tell you the minimal assumptions that you need in order for this to work. So you have some data set, which is distributed according to some distribution P. You have that minus R, comma R is a confidence interval for the mean of this distribution with coverage 1. So to say it another way, basically what we've said before, we know for a fact that mu is within some range minus R to R. No different than what I mentioned a few times before. And the other thing we need, which is kind of a very minimal assumption, is that we can compute non-private confidence intervals for the true distribution P. That means that essentially whatever this distribution is, we know kind of what the tail probabilities are like. This is a very standard assumption in, say, statistical settings. For Gaussians, we understand what the tail looks like very well. Yeah, in many settings, we understand what the tails look like. So those are the minimal things we need. And what the algorithm will be the following. The first 2 steps are going to look very familiar, what I've already told you. The third step is going to surprise you. Maybe not. Okay, the first step is clearly we Winsorize the data. The second step is that we compute the noise mean, either exactly what we've done before, but the third step where we differ is using this information we have, we get a new confidence interval for where the mean must lie, and then we iterate. So let me show you a bit more concretely. This is what we did before. We Winsorize our data or clip the data. They're the same word, Winsorize, just a statistician way of saying it. You clip your data, then you compute the noise mean. It'll be maybe here where the true mean is like maybe a bit to the left. But the really cool thing is, where did this X come from? Where did this noise mean come from? This noise mean came from a combination of 2 sources. It came from the error due to the data sampling procedure, as well as the noise we added for privacy. So in that sense, we kind of have a distribution of this point. And using the distribution of how this noise mean came up, then we can say, okay, the true mean must actually be within some narrower range. So you can see now we made some progress. We started with a wide range in terms of where the mean lies, and we've made it narrower. So this lets us essentially recursively apply this procedure, or iteratively, I guess, and then we can get another mean estimate, which is closer now to the true mean. And from there, we could draw some new confidence intervals and so on. Essentially, we keep shrinking the confidence intervals again and again until eventually we get something very narrow, and we can just return whatever the true point estimate is. So this is the whole algorithm or the whole framework. It's very simple. I'll pause here for questions, because if you get this, then you can take a nap for the next 30 minutes, 40 minutes, and you won't miss much except technical details. I think Ravi has his hand raised, and Alain, no, I see.
When do you stop iterating? Because eventually you start Winsorizing into where a lot of the data is. So how do you know when to stop Winsorizing?
Fantastic question. Yeah, that's a great question. So we'll talk about this more in a few slides, but essentially we can say in theory, you need to do this like log R times. In practice, you need to do this maybe 3 times. Yeah, this is sort of like a hyperparameter that you would have to tune in a real algorithm, in the sense that, yeah, 3 kind of work well in our experiments, but depending on your setting, you might need more or less. But yeah, you can actually compute beforehand how wide your intervals will be at each time. This is something I'm not really going to touch on, but yeah, you can determine how much error versus you want to get due to privacy versus sampling error in that sense. Great question.
And how does this work if you have heavier tails on your distribution?
Yeah, that's a good question. You can still run the same type of algorithm I haven't worked it out, but I think you might not actually get the real statistically minimax optimal rates for that type of setting, which is something which is a bit interesting to me and something I'm still investigating more, trying to understand, whether it's possible to really do unbiased estimation in these heavier tailed settings. Yeah, it's unclear whether this will be as practical in very, very heavy tailed settings, or at least in theory, whether it'll be as practical. It'll probably still be effective, I think. But yeah, I'll comment that even if you just have, say, a moment bound on your distribution, the same framework will apply. It'll probably still be reasonably practical. Whether in theory it'll give you the right thing, unclear. Cool, great questions. Anyone else? All right, so if you got this, then I'm totally happy. But we'll go into more details. The format of the rest of the talk will be get a new confidence interval and iterate. The format for the rest of this talk will be kind of telling you first about some of the theoretical guarantees and going through the algorithm in detail, and then after that I'll shift to showing you some experimental results to show how this really works pretty well. So, okay, let me tell you another theorem first on Gaussian mean estimation, which is kind of a better version of what I showed you a few slides ago. The previous one was kind of folklore. This one is what our algorithm gives. So again, we're in the same setting where we have a data set generated according to Gaussian, let's say with known variance, or you can let sigma squared equal 1 if you want. There's the private algorithm, which outputs a confidence interval, LR for mu. This just says an interval in which mu is going to lie. And if you have this many samples, let me just get both of these. If you have at least square root log r over epsilon samples, then this confidence interval has a range, essentially 1 over square root n plus 1 over n epsilon. So let me skip ahead a bit. So essentially, I think the sample complexity statement is a bit easier to read here. So remember before what we had was we didn't have this third term, but there was an r here, an r over alpha epsilon. But the key point here is that we've reduced the cost on r, that is our uncertainty, from a linear cost to a square root logarithmic cost. So this is an exponential improvement in terms of this parameter. And this is very useful if, say, you're an analyst and you have no idea where your data lies. You can just be very generous about your guess as to where it lies between 1 and a million or something. And this will be able to adapt to that fairly cheaply. Yeah. So that's the statement of the theorem. And let me, yeah, if there's any questions about the theorem statement, I guess now is the time to ask. The main thing I just want you to take away here is that the cost on R decreased a lot. Let me tell you the actual algorithm, which I sort of sketched before, but I'll tell you in a bit more detail. It's called CoinPress, which stands for Confidence Interval-Based Private Estimation. Credits to John for this title. I think that's pretty good. So the setting is we have some data set where the mean is within some range, and we have known variance sigma squared. And I'll describe it to you in sort of one iteration, and then we'll just iterate that procedure. What we do is we initialize the interval, our confidence interval, to be minus r to r, some interval where we know pretty much for sure that the parameter lies. What we're going to do is we're going to Winsorize our data set, or clip our data set, to the interval L minus sigma. Okay, so this looks a bit weird, but essentially what you do is you Winsorize it so that 99.9% of your data is going to lie within this interval. So we know, for example, that the mean is within L comma R. And so similarly, I said before that we enhance these to be plus or minus square root log n. Essentially, you just stretch this interval where the parameter lies so that you'll contain all the data. And in a Gaussian case, this won't increase the width of your data set, or your interval, too much. This should still be relatively similar. So ideally, this interval that we've created here will contain most of the data. And then we just find the sensitivity of the statistic to be essentially the difference between these two endpoints, r minus L plus 2 sigma times d of 0.999. So now what we do is we compute a point estimate of the mean. And this is in the very familiar way. You just take your data set, average it after the Winsorization, and then you add noise, which is Gaussian, proportional to this sensitivity here. But the new step, which is less familiar, is the following, step 4. You generate a confidence interval, which is centered at this point estimate. So yeah, you center at the estimate you got here. And then you account for, but you make an interval around this, which accounts for 2 different types of noise. So the first error you account for is the error from sampling. So if you're just doing like the sample mean, then this would tell you a valid for the first 2 terms here, the z plus or minus this term here. That would tell you a valid confidence interval for where the true mean lies. But then we also stretch this confidence interval to account for the error due to this added noise as well, which you notice it follows a very similar form, which is convenient because we have Gaussian noise added to a Gaussian sample. So for this, it's very simple. It could be more complicated in other settings. So what we're going to get is we're going to get some new confidence interval, and we're going to let L and R be its endpoints, and then go to step 2. Essentially, generate a narrow confidence interval, add noise to the clipped data set, and account for the noise, and keep repeating. And after several repetitions, this is related to Alain's question, which is log R iterations in theory, but maybe 3 iterations in practice, then we can output the confidence interval L comma R. And the theorem is that this is going to be both private and a valid confidence interval for the unknown parameter mu. Cool. So this is a fairly simple algorithm in the sense that it only adds more to a little bit more to the baseline algorithm. And in one slide, I'll tell you like kind of how the analysis works. Again, this isn't too important, and I'll go over it fairly quickly. But the idea is basically that you make some constant factor progress by shrinking this interval each time. So the initial interval width is going to be 2R, roughly, just because, yeah, it's going to be 2R. And after 1 iteration, the interval's width is going to be roughly this wide. This is the sort of 2 different sources of error. So the first term is the, remember, sorry, when we draw the interval, we have the 2 types of error to which make up the width of the interval. The first is the non-private error. The second is the private error. So the first term, again, is just when you do Gaussian sampling, you're going to get this 1 over square root n. And the second term is essentially what we have due to the error due to the noise introduced. So remember, I said that the noise is going to be of magnitude roughly r over n epsilon. Well, that's great, but we also have to include a square root of t, where t is the total number of iterations that we include. The reason is due to composition of differential privacy. So that'll increase the cost of privacy by a square root t factor. So the key thing to observe here is essentially this is the width of an interval after 1 iteration compared to before. And you'll notice that this term is going to be fairly small, so ignore it. But really, we want to compare 2r with this latter term here. And we notice that if we have that n is greater than square root t over epsilon, then we'll make a constant factor improvement. Say that we have like n being equal to 100 square root t over epsilon, we'll cancel this term, and we'll be left with r over 100. So you can see that we've shrunk it by a constant factor, which is, as as we see in computer science a lot, a great news, because that lets us do sub in a parameter log t somewhere or log r somewhere, and that's great. So essentially, we make a constant factor improvement each time if we have enough samples, and eventually that'll allow us to arrive at an interval which is of constant width. And from there, we can run the previous baseline algorithm. You recall this one which had complexity 1 over square root n plus this uncertainty interval divided by epsilon n, which will just be the optimal rate for this setting. Okay, I went over this fairly quickly, but don't stress it too much. Essentially, we make a constant factor improvement each time until we're narrow, and then we're done. That's pretty much it for proofs and math in this talk. I'll flash a change for the multivariate setting, but after this it should be relatively math light. So
just a question.
Yeah.
Isn't it more than a constant factor improvement for if?
Let's see how
a lot better than.
How so? I mean, yeah, I think theoretically you could, say if it's some other function of R, then you could say it makes a polynomial improvement, but that would cost, I think, a polynomial n in terms of, or sorry, a polynomial in R.
Okay.
I think this is the best sort of balancing. Either way, this is just for theory,
Sure.
and I'll mention, yeah, this is just for theory. This matches the lower bounds. In practice, there's sort of a different way that you like. If you have more samples, it would give you a better improvement anyway, automatically, without you having to do any sort of analysis. But yeah, so let me contrast this with prior. So far, I've solved a pretty simple and silly problem, which is just like one-dimensional mean estimation. We already knew this very well, so this isn't really the big takeaway, perhaps, from this talk. We had many other approaches which have been studied recently, including private histograms, which I'm sure many of you know private histograms in general, but they used it for mean estimation, Karwan Badan. And yeah, roughly it uses this sort of histogram method to coarsely estimate the mean, and then you do some clipped and noise mean to finally estimate the mean. So it's kind of like a 2-round algorithm where the second part is 1 round of our algorithm. So, and other types have been, for example, there's the do-it-all paper, which does quantile-based methods, which I won't get into, but I'll mention that this kind of is based on the fact that you can compute quantiles for your distribution, and it's sort of sensitive to that. For example, if you have non-Gaussian data, then it's not quite as clear. And these are both great approaches for univariate Gaussians, but they're not great in terms of, say, moving to multivariate settings. The reasons are kind of different for both, actually, interestingly. The first one is not great for the multivariate setting because histograms, this is, I think, like an important conceptual point, which is that histograms aren't great at capturing multivariate settings because of the fact that if you try to make a histogram in multiple dimensions, you'll hit the curse of dimensionality and pay exponential in dimension. So I think one nice contribution of our work, I think, is that it gives a simpler way to sort of deal with multivariate settings. And also, this do-it-all paper assumes a type of symmetry assumption, which can be not great in a multivariate setting. But ours fairly simply scales to this multivariate setting. And let me just show you in picture what the picture in the next slide. This is a theorem. Let me just flash it here. It's essentially saying the same thing as we said before, but instead of, since it's a multivariate problem, you have to pay something depending on the dimension. And it's kind of where you would expect to pay depending on the dimension. But I guess I promised not much more math, so let me skip over this unless anyone has questions. We can talk about it later. This is essentially what the algorithm looks like. It's essentially the same picture I showed you before, except in a multivariate setting. You start with some initial large ball, then you do the add noise and clip, and you make a smaller ball, and you clip, add noise, and you make a smaller ball until eventually you get a relatively tight ball around your data, and then you can just return the final estimate. So pretty much the intuitive picture as what you saw before, but mapped to multiple dimensions. So that's essentially the algorithm, and we have, here's the theorem, here's the outline of what the algorithm is. It's essentially the same thing as before. You can see the differences from what we did before in red. The only difference is the fact that we're working in multiple dimensions. So you clip to a ball instead of clipping to an interval. You add multivariate Gaussian noise instead of adding univariate Gaussian noise. It should not be too surprising in terms of technical details to pretty much anyone here. So I won't belabor this slide. Just wanted to show you that this is the same framework as before, and things work out simply. So let me show you now some experimental comparisons between our work and previous works. All the code is online. You can see this is at one of my co-authors' GitHubs. And let me show you what these, let me interpret these plots for you. So what we do is we compare a bunch of different estimates. The non-private estimate, so the baseline that we'd like to, sorry, not a baseline, the ideal that we'd like to compare with is the blue line at the very bottom. You can see, you can consider our approach to be this t equals 2, the red one. That essentially says 2 rounds of our CoinPress algorithm. T equals 1 is kind of the naive baseline, and KV and SimQ are Karwo-Badan and the do-it-all approach, respectively. So yeah, essentially you can compare our result, the t equals 2 case, sorry, the x-axis here is the numbers of samples, and the y-axis is the amount of error. And so we'd essentially like the line to be as low as possible. You can see that our error is pretty competitive with the non-private error, especially in comparison to all the other alternatives, including, say, the baseline t equals 1 and other previous approaches which don't do quite as well. And if you just compare, say, us with the best alternative, you can see the excess error over the non-private estimate. So 0 is kind of the best we could possibly hope for, just because that's the non-private estimate. And you can see that there's pretty significant gaps at even small sample sizes between us, or especially at small sample sizes, between us and the best alternative, which is this do-it-all paper. Let me just remind you that the do-it-all paper, they were kind of focused on the univariate case. The only way to apply the univariate case in the multivariate case for the multivariate setting is essentially doing each dimension one by one. So this kind of tells you that even if you have a very good problem, or sorry, a very good algorithm for the one-dimensional problem, doing the thing that works in theory, which is just like doing each coordinate independently and give you the right answer theoretically, that will not give you a good answer in practice. That doesn't really work. And working in the higher dimensional space directly is kind of the better thing to do. So this within 50 dimensions, similar things hold even in, say, lower dimensions. I think Alexander had a question.
Yeah, I mean, I have a question. If you do this coordinate-wise, aren't you paying square root of the dimension for this?
So
which you could explain probably the difference.
In terms of theoretical guarantee, it will be the exact same. The reason is that, okay, I mean, right. What you do is you don't necessarily estimate each to like accuracy, say alpha. You estimate each to accuracy alpha over square root d. And then, you know, for example, if you have a 1 over alpha squared sample complexity for one dimension, then putting in that square root d will give you this d over alpha squared. So that gives you still the right sample complexity in theory. Does that make sense?
Okay, so it's easier for me to think about inaccuracy. So essentially, for each coordinate, you just improve the accuracy. You compute it for accuracy divided by square root of the dimension, right?
Yeah.
But you pay the privacy budget for this too,
so,
right?
Good question. The interesting part is, for example, the middle term, which has a 1 over alpha epsilon in the 1D case, you're going to pay a square root d for the accuracy. But then since we're working with concentrated DP, you're doing d different things, one for each dimension, but you only pay a square root d because of composition, because of advanced composition, essentially. It's kind of miraculous, but the fact that you know, both the alpha and the epsilon get squared by scaled by square root d makes it so that it still gets you the optimal rates or sample complexity. In theory, at least, but yeah, in terms of practice, it seems like doing it directly in the higher dimensional space is quite a bit better, which surprised us. Yeah, in terms of experimental projects, there's sometimes the ones where you have to fight to get cool theoretical experimental results, and some where they just surprise you by how good they are. And this one, I mean, not to brag too much, but I was pleasantly surprised by how nicely this worked out to show good results.
Thanks.
Even though the theory would predict no improvement. Yeah, thanks for asking. So yeah, this is sort of a moderate dimensional setting, d equals 50. For a lower dimensional setting, you can still see that we get strikingly close to the true best non-private thing at sort of all sample sizes, low and high. And also in high dimensional or higher dimensional, this is a 500 d equals 500 setting. Just to illustrate, we compare again L2 error, where we compare our approach, SimQ, which is the previous best, and the non-private. And you can't even see the non-private here, at least for small n. You can see that in previous approaches may fail catastrophically for a small number of samples. And this is kind of like based on how the histogram works. If you think about, you know, what happens if you don't have enough samples for the histogram to work, you could get something which is totally wrong. This might be a bit technical for people who understand histogram, and only for people who understand histogram methods well. But essentially, there's a nice thing that even for small samples, we're not going to fail catastrophically. Kind of looking at the, so this is a comparison in the regime where the histogram doesn't fail catastrophically. And you can see, so this from truncated in terms of the n from 4,000 to 10,000. And you can see that we still do much better when you can get non-trivial estimates using the alternative. And the last plots I want to show you here for now are just the effect of R, because this is one thing I've emphasized a lot during this talk, the prior information that the analyst has. So by increasing the value of R, that corresponds to the analyst having weaker and weaker prior information and weaker information about what the data looks like. So what do I want to show you? We have a lot of things here, but essentially what you will have to do, remember I said you have to set this T parameter to be roughly log R, but 2 or 3 works in practice in many cases. But what we did in this case was we really set the R to be super, super large, like unreasonably large, where the true signal is maybe just like a Gaussian with identity variance, but we set R to be something like 70,000. And if you set, say, T to be 10 iterations, which is closer to, say, log R, then it seems like it can handle this pretty well. Even when you set the uncertainty to be very, very high, then you still get a low L2 error. So this just sort of shows that our method is also robust to having weak prior information about your data / distribution.
What did you set the privacy parameter to in these experiments?
Oh, let me think. It's something, it's fairly small, like something on the order of 1, maybe 0.5, maybe 2, somewhere within, what I think many practitioners would consider the higher privacy regime. Yeah, good question. I can't remember off the top of my head for these specific plots, but I think maybe it was rho equals 0.5 for CDP. Cool. So everything I've shown you so far is for mean estimation. I'm going to mention that we can also do covariance estimation. I'll probably skip over. Actually, I don't have even slides for this here. But I just want to illustrate and mention that this also works for, say, covariance estimation, which is a fairly similar algorithm, but it just has to be, it has to take into account the geometry that we get in a covariance setting. So all we do again is Windsorize, noise the empirical covariance, and then recurse this time on a confidence ellipsoid or a ball, just to deal with the geometry. Same ideas with harder math, you have to analyze some spectra, etc. And I think the kind of neat thing that I found fun in this project is in a previous work with Jerry Lee, Vikrant Singhal, and John Ullman, we had a very sort of theory way of solving this, which is not at all practical. We have some crazy constants there. It's all just for proving things in theory. But what we essentially show is a softening to make it practical, removing a lot of hyperparameters, and it's a lot simpler in terms of what we have in this paper. And it still works very well, I'll say. It's not quite as good as the mean estimation procedure for whatever reason. The mean estimation was surprisingly good. This is just, I think, good rather than surprisingly good. Here's a nice picture that John made, which I wanted to include, basically roughly showing how the algorithm works. Yeah, I'll describe this because I think if you, I'll walk you through this one. So imagine we have some true covariance, which looks something like this. And the idea is we have some sort of clipping based on what our estimate of the parameter is. So we have some big ball. And based on the size of this big ball where the covariance lies in, then we can add noise. And what this will give you is it'll give you a noise covariance, this blue thing here. But based on which is in some directions like good estimates, in some directions smaller bad estimate. Say sort of the narrow directions is not really great, but the longer directions is pretty good. But the most important thing is it'll allow you to shrink this confidence ball from something here to something which is much narrower and which is a tighter bound around the true covariance. So that's just like one picture of the algorithm. We can talk more offline if you want. But let me show you, I think, a really fun application of this, which we did for basically a PCA type application. So here's a study which was done, which appeared in Science maybe like a decade ago, maybe 2008, I think, by Novamar et al. What the researchers did was they took a genome data set, a high dimensional genome data set, and they consisting of maybe 1,000 or 2,000 individuals across Europe. What they did was they took each data point and colored that individual's data point by their country of origin. For example, blue is Spain, orange is France, and so on. And what they did was they took the PCA of this genomic data set and projected into the plane, and they got this picture that I show here, this non-private projection, which fairly closely resembles the map of Europe. So to state this in sort of simpler words, non-technical words, what they did was they did an experiment that allowed them to show that the two directions which explain most of the genetic variation in Europe correspond roughly to latitude and longitude, which was kind of cool. You know, from just genomic data, somehow you can recover what Europe looks like. Now, of course, the natural concern you might have here, there's many concerns, but one natural concern is you're doing some sort of experiments on genomic data which are generally sensitive. Like we were just playing with the toy version of this data set. There's a full version of this data set, which we couldn't even get access to because you have to be some cool bio person to do that. And so this is a smaller version. But yeah, in the sense that this is, of course, sensitive data, and just like giving this information might leak some things about the individuals who participated in it. So instead, you'd like to do it with differential privacy. And if you naively try to do it with privacy, you can see the results here. Europe is destroyed. And it doesn't really resemble the original picture at all. Like, essentially what this is doing is taking the top two principal components of the data in a differentially private manner and then plotting the data. Of course, plotting the data is not private, which some of you will recognize, but the idea is how much do the directions resemble the original directions? And you can see that the directions that we got don't really resemble the original ones. But if you use our algorithm and use more and more iterations, then it starts to pretty closely resemble the original thing. So this gives some promise in terms of this type of approach being useful for this type of exploratory data analysis application. So this was a kind of fun investigation. And so I'll conclude here in one slide just telling you we provided a generic recipe for private estimation, which is described in one slide. Just clip your data set, compute and privatize the standard estimator. Then you generate confidence intervals accounting for this noise and repeat. And I've told you just 3 places it's applicable today: mean estimation, covariance estimation, and PCA, but it's sure to be applicable in other settings as well, some of which we're investigating right now. The code is all online. If you want to play with any of it, I'm happy to answer any questions now or later. Thanks.
Thank you. I don't know if anyone has questions. So one question is that you are making some sort of assumption about the data set being Gaussian. And I sort of just wonder generically how that could be relaxed. You know, what if we asked instead to compute the median parameter or something like that? Any thoughts on how that would change things?
Okay, I guess I interpreted those as 2 separate questions. The first thing is like whether the Gaussianity is really crucial. I kind of said that you know, you can generally it works in any setting where you can have some sort of confidence intervals. Mm-hmm. So even if it's not Gaussian tails, that's okay. But it also seems to be surprisingly robust to this, in the sense that like we still apply it in cases where the data may not be Gaussian. For example, for this picture, these were generated like, this is definitely not a Gaussian distribution. I don't know what it is, but it's probably not a Gaussian. And it still seemed to work okay. So like, even though it doesn't perfectly fit the theory, it still seems to work kind of well and be robust to these types of distributional assumptions. Mm-hmm. Yeah, but you could rigorously analyze it for pretty much any setting you want based on, it's a pretty simple recipe.
Okay, if there aren't any more questions, let's thank Guatam.